Hi everyone, welcome to another episode of Coding Adventures. In this one I'm going to be attempting to make some clouds. So it all started a few months ago when I was having fun learning about Raymarching, and thought, well, I could create a cloud shape by stacking some spheres on top of one another, and then use my newly discovered Raymarching powers to blend them together. To animate it, I made the spheres change size over time, and experimented with the lighting to try and make it darker on the bottom, and have a little highlight along the top. The result was underwhelming, so I decided to do some research. It was a bit terrifying though, so months passed and I worked on other things, but every day the clouds would float past my window, taunting me. A few weeks ago I finally decided to make a more serious attempt. I started by searching for some more approachable looking papers and articles on the subject, and read through those. The first bit of insight I gained was to use something called Worley Noise to create the cloud shapes. The idea there is to scatter some points randomly inside a square, and then create a texture where each pixel stores the distance to the nearest point. So black represents a distance of 0, whereas white is the maximum distance, which I normalized to always be 1. If we invert this, we get these nice bubbly shapes, which should be good for clouds. Now, I needed this texture to be able to repeat itself without an obvious seam. A simple way to achieve this is to take the initial set of points and copy it 8 times to completely surround the original square. If we generate the texture now with the inclusion of those adjacent tiles, the texture will repeat seamlessly. I also needed the texture to be 3-dimensional, so I modified it to operate inside of a cube, with now 26 neighbouring copies. That's quite a lot of points to have to loop through for every pixel on the texture, and so understandably it was taking a few seconds to calculate. A simple optimization I read about is to divide the space into little cells and place just one point randomly inside each one. This means that to calculate the value of a certain pixel, we just figure out which cell that pixel falls into, and then the closest point is guaranteed to be in either that cell or one of the adjacent ones. My results when trying to make this tile were rather weird at first, but I eventually got it working. So the random cell points I generate in C#, and a compute buffer is created out of those, which then gets sent to a compute shader, where the value for each pixel can be calculated in parallel on the GPU. So here's my final little setup for creating the noise texture. I can specify the number of points to use, and also overlay different frequencies of noise to add some variation. Since this is a 3D texture, I added a slider so that we can choose which slice we want to look at. Now this noise is stored in the red channel of the texture, but we can store more noise in the green, blue, and alpha channels. And as recommended in the papers I read, I also have a second, lower resolution texture for adding some smaller details. I now needed a way to somehow draw these as clouds in the scene, so I started with a little test. The onRenderImage function here is called once the entire scene has been rendered into the source texture. Before it's displayed though, we can modify it with our own shader. This fragment function in the shader is run for every pixel, so for example if I sample the input texture at the current point and return 1 minus that, it will simply invert the colors. Or I could sample the texture again with a tiny offset, and if the difference between the color of that offset pixel and the current pixel is greater than some threshold, set the color to black. We've just created the world's worst edge detection effect. So now that I have a way to draw to the scene, I created a little box object to act as a container for the clouds in 3D space. I also looked up the maths for finding the distance to both sides of a box along a certain direction, so that as we're going through each pixel in the fragment shader, I'll be able to figure out where there might be clouds. I'll pass the bounds of the container to the shader, along with the noise textures, because we'll need those sooner or later. Inside the shader, I'll then get the current camera position and view direction, and use that to figure out if the view ray hits the container. If it doesn't, I'll set the color to black, which gives us this kinda cool looking mask effect. That's not what we're trying to achieve though, so I'll make it draw black instead if we do hit the box. This now draws the container on top of everything else, which is not quite ideal because it means our clouds will obscure everything. Thankfully, when the scene is rendered, the distance from the camera to the geometry at each pixel is stored in a texture. We can read the depth value from that, and I was a bit confused at first because the value you get is non-linear, I believe so that smaller values can be stored with greater precision. But Unity provides a function for converting that back to a linear value, so we can now simply say that we only hit the box if the distance to it is less than the depth value. And sure enough, the container is now drawn properly in the scene. So that's great news, but of course the real goal is to draw what's inside the box. So I'll add a function for calculating the density of the cloud at a given point inside the container. We can transform that point by a scale and offset parameter just so we've got some settings to play with, and then we can use that transformed point to sample from the noise texture. For now I'll just return the value in the red channel minus some threshold, so anything below that threshold is empty space, and anything above it is inside the cloud. The idea now is that we'll estimate the density of the cloud along the view ray by taking a few samples. So back in the fragment function, I'll create a loop where we move a little distance inside the container each time, and add up the density values to get an estimate of the total density. Once we have that total density, I'll use this equation e raised to the power of negative total density, which just describes how the more stuff that light has to travel through, the smaller the proportion of light will be that reaches us, because some of it will bounce off in other directions. So in the code, I'll call the proportion of light that reaches the camera transmittance, and I'll multiply the original color by that transmittance, which should give us black in regions of high density. As you can see, after rather a lot of work, we finally have something that resembles a cloud, if only very vaguely. We can play around with the settings, like the scale of the clouds or their density multiplier. We can also change the density threshold, which affects the coverage, and move them around using the offset. This is getting a little exhausting, so let's take a moment to watch some real clouds flowing over the mountain. Okay, enough slacking off, back to work. Clouds, I'm told, are made up of loads of little water droplets, and when light enters the cloud it kind of bounces around for a while before exiting it. Most of this light will be enjoyed by plants and cats, but some of it will end up in the lens of the observer to help form an image of the cloud. This is obviously a very complex process to simulate, so we're going to need to resort to a crude simplification. Imagine a ray going from the observer through the cloud. We want to figure out how much light travels along this ray, so let's start by taking a point inside the cloud. To estimate how much light reaches this point, we cast another ray towards the light source, with a couple of density samples to figure out how much stuff the light has to travel through to get there. Then, using our equation from earlier, we can estimate how much light will actually reach that point, because remember, some of it is going to bounce away in other directions. We then need to apply the equation again for the path along the ray to the viewer, since light might bounce away there too. We'll have to do this for a bunch of points inside the cloud, and all this gives us is the lighting information for a single pixel. Our poor GPU has to do this for every pixel that the cloud covers. Anyway, armed with this new knowledge, I set about implementing it in code. I find writing shaders extremely entertaining because, as you've just seen, rather weird things tend to happen when you make mistakes or experiment with parameters outside of their intended range. Anyway, this is the code I ended up with for stepping through the cloud, and this calls the Lightmarch function, which calculates how much light reaches the current point from the light source. I also messed around in the density function, trying different ways of combining the different noises. I don't think what I have here is particularly good though, so I'd like to do more research and experimentation there. Here's my final editor setup, so I can put the noise channel that I'm working with in the corner, and then play around with these settings and see how that affects the shape of the actual cloud. Then when I'm happy with that, I can go into the next channel and maybe isolate that in the noise weights here and just mess around until it looks okay. Then I can also experiment with combining all the channels using the weights again, and I should maybe lower the density offset to get a bit more empty space. Then for the detail noises, I have an overall weight here which allows me to subtract the detail from the edges of the clouds, and I can play around with the scale of that. Then there are also these lighting settings, so we can make the clouds darker or brighter and so on. Of course, there's also the container itself, so we can position the clouds in 3D space and scale it to make them taller or to cover a larger area. Apart from changing the scale, density and coverage of the clouds, we can make them move over time using the offsets. So this is the main shape offset, and then there's a separate one to control the detail noise. In the lighting settings, we can control things like forward scattering, which is how when the light bounces inside the cloud, it's more likely to continue roughly in the same direction than to bounce sideways, for example, which helps give us this silver lining effect looking towards the sun. As for the sun itself, we can of course change its color and rotate it around. So that's essentially what I have so far. Obviously there's so much more that needs to be done here, making nicer looking and more varied cloud shapes, having different types of clouds at different altitudes, improving the lighting, and especially improving the performance, because right now it's really slow. To end things off, I cobbled together a simple little demo using the terrain generation from my very first coding adventure video, an aeroplane model I found online, and a controller I also found online. Here it is. That's all I have for now. Links are in the description, and I hope you've enjoyed. Cheers.